Okay, here's question number 3 from the review for exam 3. Here we want to find two power series solutions about the ordinary point x equals 0 for the equation y double prime minus y prime equals 0. So our power series solutions are in the form y equals the summation as n goes from 0 to infinity, c sub n, x to the n. And then when I substitute in for y prime, I'm going to use the sum n goes from 1 to infinity, c sub n times n, x to the n minus 1. And I'll substitute in for y double prime the sum as n goes from 2 to infinity, c sub n times n minus 1, x to the n minus 2. So we're going to substitute these into the equation, and then we'll work to combine all the summations to a single term, just like we did in question number 2. So y double prime, that's sum n goes from 2 to infinity, c sub n times n minus 1, x to the n minus 2, minus y prime, the sum n goes from 1 to infinity, c sub n times x to the n minus 1 is equal to 0. That's what we get. So notice there are no x's outside of either summation. So our first step is going to be to look at those exponents, and that's going to be our k for each summation. So my first summation, I'm going to let k equal n minus 2, and that means n is going to be k plus 2. And when I write this first term, I'm going to get the sum as k goes from 0, because when n is 2, you get k equals 2, take away 2, which is 0, to infinity, c sub n is k plus 2, times n k plus 2, times m minus 1 is going to be k plus 1. It's k plus 2, take away 1, and then x to the k. On my second summation, we're letting k equal n minus 1. So n is going to be k plus 1. And we get the sum as k goes from, let's see, n starts with 1. So I get 1 minus 1 is 0. Oh, how nice is that? Notice that we have the same lower index. That's beautiful. Times c sub n is k plus 1, times n, which is k plus 1, x to the k equals 0. So for combining summations, remember there were 3 rules. Any x's outside of the summation need to come in and need to be combined with that x to the n, or whatever the power is that you had. And then secondly, you take that power of x and replace it with k. And that will change all of your variables from n to k. And then thirdly, you look at the lower index. In this case, we have k equals 0 for both summations. If the lower index does not match, then you need to remove terms until you come to a common lower index. Sometimes you need to remove one term, like we did for problem number 2. Sometimes you might need to remove 2 or 3 terms. It just depends. So here we can combine. And when I combine, we're going to have a common x to the k that will factor out is still inside of the summation because it involves k. Anything that involves k has to stay inside the summation. And when I factor that x to the k out, yeah, that's fine. I have c sub k plus 2 times k plus 2 times k plus 1 minus c sub k plus 1 times k plus 1. And that's equal to 0. Let me close my brace. So notice that for our power series is the power on the x. Involves a power on the x. Our power series solutions right here will look like when n is 0, we get c0, x to the 0. When n is 1, we get c1, x1. When n is 2, we get c2, x2, and so forth. These c's are defined by everything that I have inside braces here. This is going to form my recursion or recursive formula. I think recurrence relation. Yeah, in terms of series, it's also a recursion formula that shows up because the in this case the k plus 2 term will be defined in terms of the k plus 1 term. And the recurrence relation defines the coefficients of x to the k. Right there. So we have x to the k times, and then everything inside the braces is the coefficient for the x to the k. And what we want to do is we want to find out what those coefficients are. What is C0, C1, C2, C3, and so forth? So I'll bring that out. I'm going to bring out the recurrence relation. I think for space purposes, I'll do that to the right here. And that gives me C sub k plus 2 times k plus 2 times k plus 1 minus c sub k plus 1 times k plus 1. And because our series is equal to 0, then we know that all of our coefficients of each term have to be 0. So we're going to set this equal to 0 and then solve. We solve for the highest index. K plus 2 is higher than k plus 1. And I'll just write that here. C sub k plus 2. If I solve, I have to bring that k plus 1 term over to the right side of the equation. That's going to give me, I'm going to write this as k plus 1 times c sub k plus 1, and then divide by this coefficient of c sub k plus 2, which is k plus 2 times k plus 1. Notice that the k plus 1's cancel, and this is true for k values 0 to infinity. So this is true for k equals 0, 1, 2, and so forth. So let me just rewrite that over here. In reduced form, we have c sub k plus 1 over k plus 2, where k is 0, 1, 2, and so forth. And we're going to use this recurrence relation to find the coefficients of, let's say, the first 6 terms. So that would be C0, C1, all the way to C5. So we'll calculate up to C5 and see what our solutions look like. So for k equals 0, substitute in to the recurrence relation, and we get c sub 2 equals c sub 1 over 2. So I'm going to box that up. And maybe I can do k equals 1 here. For k equals 1, I'm going to get c sub k plus 2, that's c sub 3, equals, when k is 1, I get c sub 2 over, and then k is 1, so I get 2 plus, or 1 plus 2 is 3. I get c sub 2 over 3. But notice we have c sub 2 defined previously. So I'm going to say this is 1/3 times c sub 2, and c sub 2 is, let me write that as 1/2 c sub 1. That gives me c sub 3 is 1/6 c1. Okay, so I have c3. I need 2 more terms. Let's do k equals 2. When k is 2, I'll get a c sub 2 plus 2 is c sub 4 equals c sub 3 over 4. But we know that c sub 3 is 1/6 c sub 1. So that's going to be 1/4 times 1/6 c sub 1, or c sub 4 is 1 over 24 c sub 1. And I think I can fit the next one here. So for k equals 3, we're going to have c sub 5, and that'll be equal to c sub 4 over 5. So notice that if we wanted to, we could come up with a formula here, because all it's doing is adding an extra factor in the denominator. Notice that for c sub 2, we get 2 in the denominator, which is 2 factorial. C1 over 2 factorial. For C3, 6 is 3 factorial. So you get C1 over 3 factorial. For C4, 24 is 4 factorial, and so forth. So you can see a pattern that's showing up. Anyway, we're going to write this out not as a single summation, but term by term. We're just going to list the first 6 terms. C sub 5 is 1/5 times C sub 4. C sub 4 is 1 over 24 C sub 1. So that gives me 1 over 120 C sub 1 equals C sub 5. So my power series solution looks like this. C0 x to the 0 plus C1 x1 plus c2 x2 plus c3 x3 plus c4 x to the fourth and plus c5 x to the fifth, and then that continues on. I'll stop at c5 because that's as far as we went for calculations. When I substitute in values for C0, C1, C2, C3, and so forth, I get, notice we don't have C0 anywhere. So I'm going to keep C0, and that's just times x to the 0, which is times 1. And then C1 is just C1, so I get plus C1x. And then C2 is C1 over 2. I'll write that as 1/2 C1, and that's x squared, plus C3 is 1/6 C1. That's my x to the third. And then plus C4 is 1 over 24 C1, x to the 4. And then my x to the fifth is 1 over 120 C1. Plus, and so forth. Now my two linearly independent solutions come from grouping my C0s and my C1s. I only have one C0 term. So I'm going to write that as C0 times 1. And then all of the other terms contain C1. So I'll factor out the C1, and I'll have x plus 1/2 x squared plus 1/6 x to the third plus 1 over 24 x to the fourth plus 1 over 120 x to the fifth, and then that continues onward. So here's my y1 is just 1, and my y2 is everything that I have inside parentheses here multiplied by C1. X plus 1/2 x squared plus 1/6 x to the third plus 1 over 24 x to the fourth plus 1 over 120 x to the fifth, and then plus, and I'll continue that on. So this is what we were asked for, two solutions, and it was implied linearly independent solutions to the differential equation. So that's question number 3.